Alright, this video is about exponential growth. In our book it's section 8.1. I'd like to start with some definitions. An exponential function involves the expression b to the x, where the base b is a positive number other than 1. Okay, so that's the basis for an exponential function. Now we want to talk about an exponential growth functions, and they are of the form y equals a times b to the x, where a is greater than 0, so that means it's got to be positive, and b is greater than 1. Now there's subtle differences between exponential functions and exponential growth functions. Okay, and as you think about it, I think you'll realize that to say that b is positive and it can't be 1, well, this is going to include bases like 1/2, which is positive but it's less than 1, up to something right before 1, like 15/16, and of course numbers that are bigger than 1, because all we're doing in this definition here is excluding the number 1. We're saying it's positive and it can't be the number 1. Whereas if the b is greater than 1, so we're throwing out some values that we have up here for b that we don't have here, and that is the proper fractions are thrown out. Positive proper fractions are included in exponential functions, but they're not down here. So when we talk about exponential growth functions, then b has got to be greater than 1. Okay. Other things that we need to know in this section is what an asymptote is. It's a line that a graph approaches as you move away from the origin. So in other words, as you pick x values that are getting greater and greater and greater, then or smaller and smaller and smaller, the graph is going to move away. Excuse me. The graph is actually going to approach this line, and that is as you move away from the origin in either direction. It could just be one direction. Alright, in general, the form of exponential functions is y equals a times b to the x minus h and then plus k. Now we've seen this minus h and plus k before in quadratic functions, and so they're going to have basically the same function here as they did in quadratics. But this function here has a horizontal asymptote, and that's the word at there. You can't see it because it's behind there, at y equals k. So that's where this is going to have an asymptote. Okay, general instructions about graphing these exponential growth functions. To graph an exponential function in the general form, what you want to do is you want to take the exponent x minus h and you want to set it equal to 0, and you solve that so you come away with x equals h on that one. Let that be your middle number of, say, 5 x values. Now I'm going to clarify 5 here because you may be able to do it with 3 values, and we'll be more explicit in that in the next screen. But just like we did graphing quadratic functions, we took 5 values and we put the vertex in the middle. And we're sort of just doing the same thing here. We're getting what I'm calling a point that's in the middle of the turn, and we're just picking points on either side of that enough to make the graph. Okay, I know some instructors do this with just 2 points, and I'm convinced that we don't want at least to do 3 or 4. Okay, moving on, graph enough points to what I call make the turn. If after graphing these points on your graph has not made the turn, then add points on whichever end needs more points to make a complete graph of the exponential function. And we'll talk more about that in a minute. Okay, next screen. Alright, I'm going to scoot over here to the next screen and include this little talk about domain and range of a graph. Okay, so what I have right here is the graph of y equals 2 to the x. Okay, when we talk about the domain of a function, it's the portion of the x-axis that the graph involves. Okay, so let's take a look at this, and we see that this graph right here, and you see the little arrow right here, that this graph is going to go on and on forever. It's getting ever closer to the asymptote, which is y equals 0. On this one, the k, there is no number k here, so we say that the horizontal asymptote is y equals well, you can imagine a plus 0 here. So y equals 0, and that's the x-axis. So this graph is getting closer and closer to the x-axis, although it never touches it. And that's what it means for a graph to have an asymptote. Okay, now on this end, we see it goes on forever. And if you think about this, it's going up pretty steep line here. This incline is really steep. We can tell you this, that this graph never gets perpendicular to the x-axis, and so it never stops moving to the right because it never goes straight up. Now, since we have infinity to go to, then we can attain whatever positive value we want to just by going up as far as we need to. So since this never stops moving to the right, then there's no end to where this graph is going to go. So we say it's going to move forever to the left or to negative infinity, and it goes forever to the right to positive infinity. And so we say that the domain then is all real numbers. And now in my class we're going to use the capital script, and I'm going to have to make that line a little bit thinner. Boy, that doesn't look good at all. Let's try that again. And let's pick us a smaller line here. There we go. So you can use the capital script R, okay, which is going to look something. No, that's still not small enough. Pick this one right here. Okay, so you can use a capital script R to represent the all real numbers. Okay, that'll be fine for my class. Okay, let's get over here to the range. The range of a function is the portion of the y-axis that this graph involves. Okay, so if you think about this, let's see, that's talking about how far up and down. Now, will we ever get into the negative numbers? Okay, well, if you think about the meaning of the asymptote, that means that this graph is never going to reach whatever this is, and this is y equals 0. And if it never reaches it, it'll never go beyond it either, and so it'll never get to have any negative numbers, and in fact it'll never be 0 because our horizontal asymptote is y equals 0. So we know it's going to always be above that, so we say that the range is y is greater than 0, and we typically use an inequality to define what the range of a graph is. Okay, so that's domain and range, and those are things that we usually talk about on every one of these graphs. Now I'm going to back up to the first example, okay, and we're going to do quite a few of these, and some of these are unnecessary, but I want you to get a feel for what these graphs are doing. So here's what we do. We're going to take this x and we set it equal to 0 and solve it. So x equals 0, and you know, it's already solved. So we're going to put that in the middle, and then we're going to try points on either side. So if we put in 0 for x, we get 2 to the 0, and that's going to be 1. If we put 1 in for x, we get 2 to the first, and that's going to be 2. Now let's graph these as we go. Okay, we have the point 0, 1 on our graph, so I'm going to go ahead and put a point there. And we have the point 1, 2 on our graph. Okay, that's that point there. Let's put 2 in. 2 squared is 4, so the point 2, 4 is on the graph. And we put 3 in for x, we get 2 to the third, and that's going to be 8. And we have the point 3, 8 on our graph. Okay. Now, as you can see, this graph is really climbing or getting steep very quickly on this side. Okay. All right, now let's put in -1. Now 2 to the -1, well, that's going to be, if you think about that, 2 to the -1, we'll put that right here. That's going to equal 1 over 2, or 1/2. So at -1, we're at 1/2, right in here. And then 2 to the -2, that's 1 over 2 squared, and that's going to equal 1 over 4. So that's 1/4. At -2, we're at 1/4. Okay, it's about in there. At -3, or 2 to the -3 power, and that's going to equal 1 over 2 to the third power, or 1 over 8. So we have 1/8 here. Okay, so at 3, it's at 1/8. And you know, on this graph, you can just hardly see the difference or the space between it and the x-axis. Okay. All right, so what we do is we kind of draw a line, and we'll maybe start what what might appear to be on the x-axis, but it really isn't, and then it's going to slowly but surely go a little bit higher and higher as we come through here. And I don't know how good I'm with this graph here, but anyway, I'm trying my best to make a smooth line through here. And we know it never goes straight up, so that would be incorrect. And then we'll sort of put arrows on each end of this. Okay, so that's really a kind of a rough looking curve there, but that's the best I can do with the equipment that I have here. Okay, now I want you, in my class, I want you to label the horizontal asymptote, or at least tell me what the horizontal asymptote is. Nobody wants to spell both of those long words, but the horizontal asymptote is an equation of a line. It's a horizontal line. It's y equals the k value, and you can imagine plus 0 at the end of this if there's nothing there. So it's y equals 0, and we usually dot it in. And of course, if I put a dotted line on top of a solid line, you wouldn't see the dots, so I'll just kind of extend that a little bit. So there's my horizontal asymptote, y equals 0. We want to talk about the domain, and we just did that on the screen before this, and we decided that that was all real numbers. And the range, and I'm just going to abbreviate that with just r, is how much of the x-axis is used, and we said that on the, again, we answered this very same problem on the screen before this, that y is always going to be greater than 0. Okay, so here's what I want to talk to you about making the turn. If you can kind of look at this graph, it almost looks like it's a 90-degree turn. Of course, since it never goes straight up, we know it never does actually become a 90, but it's kind of like a curve here. Okay, that's kind of making the turn is what I say. And what we get when we take our exponent and set it equal to 0 is we get a point that's, I'll just say that's somewhere about halfway through that curve. Okay, so on the right side of this, typically, not with everyone, but typically, that graph starts to climb or goes up in a hurry. That's my dog in the background. I'm not going to let her outside. And on the left-hand side of that thing is dropping down to the asymptote, and it's not going very fast at all. It's dropping very slowly. So going down slowly, going up fast, and we want some on either side of that before we say we have a complete graph of this. So that's going to be, that's what I talked about earlier about making the turn. I want to see some points to the right of this that are going up real fast, and to the left of this where it comes down very close. Okay? All right. We looked at that screen, and I'm going to have you try this problem, and we'll see how we do. All right, let's see how you did here. We put quite a few points in here, and of course we never were able to use this one because it was too high, but the rest of these, and I don't know if I went out and did this one or not. I don't think I used this one either. So we're using 1, 2, 3, 4, using these 5 points, and we put this on here. And the domain is all real numbers. The range is y is greater than 0. Horizontal asymptote is the line y equals 0. And there's the graph. So hopefully you did okay on that. Now I'll tell you, I think I would have accepted this with this group of points right here. That would have certainly been enough. If you think about it, once you get down to 1/3, that thing's dropping pretty quick here, and then going from 1, 0 up to 0, 1 up to 1, 3, that's already getting pretty steep. We could kind of project where that was going. So I'm going to say that you probably could have done that with 3 points. Okay? All right, well, let's take a look at this. Now, keeping in mind that we're dealing with the general form y is equal to a times b to the x minus h, and then plus k. That last problem didn't have an h or a k in it, really, or an a. It just, well, it did, but it was 1. So here we're going to throw in a number, 1/2, okay? And then, of course, is there anything that's coming after the x up here? Still no h and still no k, and we'll develop that as we go, okay? All right, so we're going to take the exponent, set it equal to 0. So 2 to the 0 is 1, and 1 times 1/2 is 1/2. So we have the point 0, 1/2 in here, all right? Go ahead and put that point in. Let's put in 1. 2 to the first power is 2. 2 times 1/2 is 1. So we have the point 1, 1 after that. Now, still not rising very quickly. Let's put in 2. 2 to the second power is 4. 4 times a half is 2, so we have the 0.22. It's going, starting to get a little quicker moving up, but still not enough for us to stop going in this direction. And we put in 3. We have 2 to the third, which is 8. Half of 8 is 4. And the 0.34 is on our graph. And now I look from there to there. Now I'm starting to get pretty steep, so I'm satisfied with this side of the curve. Now let's do this shallow side, and let's see how many points we need to do here. If we put in -1, 2 to the -1 is 1/2, and 1/2 times 1/2 is 1/4. And -1, 1/4. And that's really going to be enough points for us to graph this, so we'll go ahead and draw it in. Come what appears to be on the x-axis, but we know it's really not. Theoretically, it doesn't touch it because it's asymptotic. And it seems like the slower I draw this, the wigglier it gets. But anyway, that thing's going to sort of come off like that and go on up. Forgive the unstraightness of that. Okay. Now, so dotting the axis of horizontal asymptote, which is y equals 0 for the horizontal asymptote. I want you to label that. Talk about the domain. It's going to go on forever to the left and forever to the right. So it's all real numbers because we'll never stop going this way. And although it doesn't go very quickly to the right, it's never going to stop moving to the right. We said it never goes straight up. And the range is y is greater than 0. Seems like that range was the same thing for the last one too, wasn't it? Well, that's because we don't have any h and k in here. Once we change those numbers, we'll see a little change in this. All right, so we're going to do that with those 5 numbers there. And I'll get you to try this one. All right, check your answers with this right here. Again, I did this with 4 points. I'll even say that 4th one over here. This one's sort of questionable, but we did 4 this time. Domain is all real numbers. The range y is greater than 0. And horizontal asymptote is this line y equals 0. Let's go ahead and label that. Okay. Next screen. All right, example 3 now. You notice that we've got a number that comes after the x and the exponent. So there's our h, and then we have a k here, and we have an a here. So we're going to have kind of a complete problem here with all the variables represented. Okay, so the first thing we do is we let the exponent equal 0, and we solve that. And to solve that, we add 1 to both sides. We get x is equal to 1. So that's the number that we start. And when we put 1 in, of course, that turns that to 0. 2 to the 0 is the number 1, because anything to the 0 is 1. 1 times 3 is 3. And then 3 minus 4, -1. You can do that in your calculator. And I'm going to go ahead and graph that point. 1, -1. All right. Now, when I have a k here, I probably want to take a minute to go ahead and write down what the horizontal asymptote is. That's y equals the k number, which is -4. Now that's a horizontal line through -4. So we'll go ahead and dot that in. That's the line that this graph is going to approach but never touch. Okay. All right. And let's go a little bit bigger. Let's see if we put in 2, we go up 1 from that. If we put in 2 here, 2 minus 1 is 1. 2 to the first is 2. 2 times 3 is 6. 6 minus 4 is 2. So the point 22 is on this curve. That's probably going to be enough in that direction. Let's move in this other direction. 1 less than 1 is 0. And if I put 0 in for x, 0 minus 1 is -1. 2 to the -1 is 1/2. 1/2 of 3 is 3 halves, and that minus how many halves is 4? It's going to be 8 halves. So we have 3 halves minus 8 halves, or -5 halves. Now that's -2.5. So 0, -2.5. Okay, you can do that on your calculator if you need to. And we're still not down to our asymptotes. Let's go a little bit further. We might even go further than our graph allows us here. If we put in -1 here, -1 minus 1 is -2. 2 to the -2 is 1 over 2 squared, and 1 over 2 squared is 1/4. So we have 3/4 minus how many fourths is 4? 16/4. 3 fourths minus 16 is negative 13 fourths. That's negative 3 and 1/4. So at negative 1, negative 3 and 1/4. Okay. Well, let's go one more. Let's go to negative 2. I'll just stick it in up here. I know it's not in order. Negative 2 minus 1 is negative 3. 2 to the negative 3 is 1/8. And so we have 3/8 minus how many eighths is 4? 32. And that's negative 29/8. Okay. Or that's going to be, let me see, that's going to be 3. It's 24. So that's negative 3 and 5/8. Okay, so at negative 2, negative 3 and 5/8, so that's past halfway, right about there. That looks like enough there. So we'll go ahead and draw in our line. It comes in here, starts rising, gets quicker here. I say quicker, it's getting steeper, and it goes on forever in that direction. Okay. Y equals negative 4. Now, let's talk about the domain. The domain is how much of the x-axis. I see it going on forever in both directions, so that's going to be all real numbers, script R, capital R. The range, now the range is going to be different because we've got a k number. We said that's going to affect the range. Well, if you can see, our graph is never going to drop below negative 4. It'll always be above it and never will touch it, so we have y is greater than negative 4 is the range. Okay? You try one of these. Okay, we'll check your work against this graph here. Horizontal asymptote was y equals k or y equals 1. There's our horizontal asymptote. And we took our exponent, x minus 2, and set it equals 0 and solved. That gave us our starting point. And when we plug 2 in, we get 3. So 2, 3 was our first point, and then we went 1 on that side, so we went to 3 and we got 7, and then we moved to the left of that and we get 1, and that's 1 2/3 here. See if I can make that look like a 2 more. 1 2/3, and then 0 was 1 2/9. Okay. All right, give this one a try. All right, well, I hope you noticed something a little different about this one, and the thing that was different was our A number. Okay, in our original definition, we talked about exponential growth. We said that A had to be positive. Well, here, A is negative. Now, that doesn't change the fact that this is an exponential function. It's just not an exponential growth function because A would have to be positive. But we still have these kinds of problems, and if you'll notice, the net effect of that was that it kind of inverted our graph. It kind of flipped it from going up this way and kind of rotated on that axis of I'm just going to say axis. It's a asymptotic, so it kind of flipped it over that right there, and now it's going down instead of up. It's an exponential function. It's just not an exponential growth function because it doesn't meet the criterion where A is greater than 0. Okay. All right. Moving on. All right, we're now going to talk about a growth function that has what we call a growth factor in it. Okay, now a growth function, when a quantity increases by a fixed percent each year or any other time period you could pick, the amount y of the quantity after t years can be modeled by this equation here. Now let's call your attention back to the original definition of growth function. It said that we had a positive A and that this was a number greater than 1. Well, think about this. If R represents an increase, we're talking about things that increase, a percent, this number would never be negative. And if you're adding that to 1, then the results of this, or that's our base right here, it's being raised to the t power, this B, by the way we set it up, can never be less than 1, and it can't even equal 1 because this is a percent of increase. It's got to be positive. So really, this is another way of writing it, and we're going to look at it as 1 plus R, and that R, okay, where A is the initial amount and R is the percent increase expressed as a decimal. So this has got to be a decimal, percent change to decimal. You remember you move that 2 places to the left to change from percent to decimal. And we call this quantity here, r plus 1, is called the growth factor. Okay, let's move on. Okay, here's example number 4. In January of 1993, there were about 1,313,000 internet hosts. During the next 5 years, the number of hosts increased by 100% per year. Now that's a pretty big increase right there. All right, so we're going to do 3 things with this question, and these will be typical questions on the test. First, we're going to ask you to write a model giving the number h in millions of hosts and t years after 1993. We're going to graph that, and then we're going to see is going to be we're going to estimate the year where it reached 30 million. Okay, so let's do part A right here. So we're going to start with our new and improved, I'll call, definition of what a growth function is in this 1 plus r form. And notice that we're calling A 1.313. Well, we started out with 1,313,000. We're going to use 1.313, and of course we know that that's going to be an answer, or that's in millions, so we've just written that a little bit smaller, and we're going to call it millions, and so our answer is going to be in millions. And then 1 is 100% changed to a decimal. You move the decimal 2 places over, you get the number 1. Now think about that. What if this was 150%? What would our number be here? It would be 1.5. If this was 85%, we'd have 0.85. If it was 4%, we'd have 0.04 here. So that number can change quite a bit. Time we're just going to leave as t. Okay, so when we plug the number in for A, again this is in millions, we have 1.313 times parentheses 1 plus the 1 from the 100% was there, so we add those together and we get our final answer over here to A, the function as a model or an equation for it. All right, let's do B on the next page. Okay, so here's our answer from A. Now we want to graph this here. Okay, so again we're going to take our t. This should say t and not x here, so let me go ahead and change that. Okay, we take our t, and I want to start with that in the middle, and if I put 2 to the 0, then I get 1, and then 1 times this number. And for our graphing purposes, we're going to round these off to 1 decimal place, so that's going to be 1.3. All right, let's go ahead and graph that. And I think I put this in the wrong spot. Yes, because let me explain why I'm going to move this. As I look over here, there's really no need for us to have any negative numbers here, because we're talking about at a point starting in 1993 and moving forward 5 years. Well, that wouldn't ever go negative. Okay, so we're going to let this first one be put down here, and we'll put it as 1.3. So at 0, we're at 1.3. Now as I look at this graph here, I have 3 lines that equal 10, so each one's about 3 1/3, so 1.3 is going to be about 1/3 of the way up, so I'm going to put that point right there. Now in years since 1993, 0 would correlate to 1993, and 1 was 1 year after 1993, or this 1 would represent 94, 95, 96, 97, 98, 99, like that. Okay? And on the side we have millions, so 10 is not 10, but it's 10 million, 20 million, 30 million. Of course, the question asks us about 30 million, so we had to have at least that much on our graph. All right, so let's move forward. Let's go with 1, and I think I've got these numbers written down here that I can put them in a little quicker for us. That's going to be, well, don't seem to find that, so let's go ahead with, that's going to be, I think, 2.6. Okay, when we plug in 2, we're going to get 5.3. You can do this on the calculator. And we plug in 3, we're going to get 10.5 rounded to one place. We plug in 4, we get 21.0. 5, I think, puts us off our chart. So let's go down here and graph these, and we go, there's 0, 1.3. At 1, we're at 2.6 now. That's going, remember, up here is to 3, so 2.6, well, that might be somewhere right in there. At 2, we are at 5.3. So where's 5.3 on this thing? Well, that's about halfway up to 10, so I'll put it right in there. That's halfway up. At 3, we're at 10.3, so we're just above the 10 line there. And at 4, we're at 21, so we're right above the 20 line there. And I think at 5, let's see, let's go ahead and put 5 in there. And at 5, well, I'm going to change my mind. I don't think we need 5. So let's just go ahead with the ones that we have here. Okay, and now we graph it. So it's going to come through here. It's going to start getting bigger here, running through these points. And something like that. Okay, now it's going to go on forever in this direction. We didn't do anything past 1993. Now, to answer the question that they asked us earlier was that at what year did it eclipse or go past 30 million? So that would be this line right here. So we follow 30 million over to here, and then we follow it down to our graph, and we're at this point right here. So 93, 94, 95, 96. This is the beginning in 1997. This is the beginning in 1998. So what year are we in? Well, this would be the year 1997. We don't know what part of the year. I'd say, if I had to guess, that looked about halfway, or say June. But they're just asking for a year, so we'll say 1997. Okay, get you to try one of these. All right, in 1980, about 2,180,000 U.S. workers worked at home. During the next 10 years, the number of workers working at home increased by 5% a year. Now, this last problem, we had a pretty big percent increase. This time, 5%, not going to be all that big. And we want to go for 10 years. So just to kind of get you started on this, it's probably not going to be a really steep one because this is a small percent increase. And if we're going to do it for 10 years, do we want to do 10 entries to our graph? I don't think we need to, so let me suggest that you start with 0 and just go every 2 years on this, so we're all kind of doing the same graph. So write the function, graph it, and use that graph to estimate the year when there was about 3.22 million workers who worked at home. Okay, I'll stop the video and you give that a try. Okay, well, go ahead and check your answer. I want to check the chart first. Again, this should be t right here instead of x. And the question is, when did we get to be 3.22 million? Again, this is millions here. So 3.22 would be right around in here, and it looks like we hit one of these almost right on the money. I think that was 3.2, so it's about 3.2. So what would 8 represent? Well, 8 years since 1980, or 1988 is the answer to that one. Okay? All right. Now I'm going to talk to you about compound interest. Okay? Compound interest is an exponential growth function of the form a equals p1 plus r over n raised to the nt, where p is the initial principal, r is the annual interest rate changed to a decimal, and n is the number of times a year it's compounded. So a is the amount in the account after t years. Now, if you think about this, this still does fit into the definition of exponential growth because it's 1 plus something that's going to be positive. So that's definitely going to be greater than 1. And this is just a product. So, rather than just t, it's n times t. So it all fits into that. So let's take a look at our example 5. You deposit $1,000 in an account that pays 8% annual interest. Find the balance after 1 year in the interest if the interest is compounded with the given frequency. A, annual. Now, annual is once a year. Quarterly, like you would think, 4 times a year, 4 quarters in a dollar. And then daily, 365 days in a year. And we'll see how these work out. Okay, so we're going to do these out here. And so for annual, so we go ahead and fill in our numbers. That's equal to 1,000 times 1 plus our interest rate was 6%, I believe. Let me check my numbers here. 8% for this one. So it's change to a decimal, 0.08 over 1 raised to the n. The number of times compounded in a year is 1 times the number of years. And for our problem, that's 1 as well. So we have 1,000 times 1.08 raised to the first power. And of course, that's just going to be mental math there. We'll move our decimal 3 places over, and we'll get $1,080. That's how much is in the account if it's compounded once a year. Okay, let's do quarterly. So A is equal to our initial amount that we put in, 1 plus our interest rate changed to a decimal, divided by quarterly is compounded 4 times a year, and that raised to the 4th power. So we're going to have 1,000 times, now that's going to be 0.02, so it's 1.02 raised to the 4th power. And if we put that into the calculator and round it off to the nearest cent, since we're dealing with dollars, we'll round off to the nearest cent. I'm going to skip that step and just tell you what the answer would be, and that is $1,082.43, rounded off to the nearest penny, and that would be to the nearest hundredth. And for daily, well, of course, A is equal to 1,000 times 1 plus 0.08 divided by 365 raised to the 365 times 1. Well, that 4 was times 1 as well, but it turned out to be 4. And I'm really not sure what this turns out to be, except for if we plug this into the calculator, it's going to give us $1,083.28, rounded to the nearest cent. So if you had your choice of when it's compounded, as you can see, the more times it's compounded, the more interest that you earn. And if we're talking about really large sums of money, that those differences, although they seem to be minute with $1,000, if you're dealing with millions and billions, why then this is really significant. Okay, here's one for you to try. All right, let's see how you did for annual. There's what it sets up to be, and then it comes out after you plug it into the calculator to be $1,590. Quarterly, we get $1,592.05, rounded off to the nearest penny, and daily, $1,592.75, compounded daily. Okay, well, that ends this video. I appreciate you watching.